Dear students, so this is the continuation of the chapter 18. In previous video I have talked about 18.1 and 18.3. In this video I'm going to talk about 18.4, which is magnetic field. So you know that magnetic field is the region around a magnet in which body of magnet material experiences a magnetic force. As you can see here, this is a magnet, and when the iron fillings has been kept here, they are directed in particular direction. Why? Because this iron fillings, which is a magnetic material, experiencing a force, so that they are aligned in that direction. So magnetic field is invisible, you cannot see this. Okay, if you want to visualize it, you put some magnetic material and you will see how they are arranged themselves. Okay, so these lines are called magnetic line of force. Now there are certain patterns which you're going to learn about here. So like here they are asking you one investigation that if I want to know how the magnetic field lines actually are there, you can use the bar magnet and compass. Okay, so let's see about if you have a bar magnet like north and south this, and if you're putting compass. Okay, as you can see here, this needle, which is this part is north side, it is deflected towards the magnetic field lines, and this is the south pole which is attracted to the north pole side. They have certain pattern. So how the pattern is there, let's see this final picture. Okay, so if this is the north pole, this is south pole, and here the compass. So if you can see, there's a pattern. This is the north side of the compass, which is going away from the north pole, but see the direction how they are deflected. So they are patterns. So this is telling you that magnetic field lines start from north pole and it enters to the south pole. Okay, so this is the few lines. Whenever you are drawing magnetic field lines, you should be knowing that magnetic field lines are directed outward from north pole and towards the south pole. Very important point. Whenever you draw this, you should always keep in mind. Magnetic field lines do not cross or intersect each other, never ever. Second point, to represent a strong magnetic field, the lines are drawn closer together. So field lines drawn further apart represent the weaker magnetic field. Now let's see, this is the actual compass needle. Again, I just now told you, if this is your north pole, this is how you look, that the south pole of this bar magnet will be attracted towards this, and this is how the magnetic field is looking. This tell you that it is originated from the north and it is entered to the south pole, which is very clear from this experiment. Now with different magnets there will be different patterns. So what happened when you have put the two unlike poles? So from the north pole it is going to outwards and it is going to enter towards the south pole. So this is the actual direction what you will see with iron fillings. Okay, so whenever the unlike poles are there, this should be the perfect direction. Now what happened when we have two like poles? They repel each other. So this is the north pole, this is the north pole. As you can see here, they will going outward, and here X, there is no magnetic field here. Okay, so this point is called neutral point. So here there is no magnetic field is experienced here. So there is no effect. They cancel out each other and there is no effect. Okay, because as you can see here, this point is going no top and this is going below, so overall there is no effect. Final they are cancelled. So what is neutral point? Neutral point is a point where there is no magnetic field is observed. Even though magnet is placed, the total magnetic fields are cancelled out and there is no magnetic field will be observed. Now what happened when we have a pattern? Okay, so you have put north pole in the two magnet, you have one magnet here, one magnet here. So okay, the direction is fixed, that field lines will always go away from the north and towards the south pole, like how you are seeing that, like here. Now if you put in reverse direction, the north pole is going to give the magnetic field lines will enter to the south pole, like this. Okay, so these are the certain patterns, you should be knowing this part. Now why I'm explaining you, because these are used further for the magnetic shielding. As the name suggests, that what is happening here, you want to shield the magnetic effect. Okay, Why it is important? Because in the hospitals, the MRI instrument or computer hard disks which are full of magnets, okay, and if some magnetic fields are present over there, they can disturb the function of these important appliances. So to prevent the surrounding magnetic field from reaching the sensitive area of this, we use the magnetic shielding. So how we do? Let's see that. So in magnetic shielding, a thin set of iron, which is a soft magnetic material. What are soft magnetic material which can easily magnetized? Iron or nickel iron alloy. So this shielding we made a particular material which is iron or the soft iron nickel iron alloy. Okay, why they are used? Because they are good magnetic in metals, and they can divert the magnetic field that are present here. You might heard of the short circuit in the electricity, where what happen if you give the electron a shorter wire, even though you have bulb, it is not going to blow because the current will just pass through the wire. Okay, similarly here we are seeing the same effect, that if you give the soft iron, the magnetic field whatever is there, it is not going to disturb the MRI or the instrument, because they all go to the prefer to the soft iron sheet. So let's see how. So this is the two way, one way here and this is second way here. Okay, so how this diagram? This is a magnet, okay, which I have put for the shielding purpose. So point number one, magnetic field lines coming out of the north pole, as you can see here, prefer to pass within the soft iron sheet rather than through air. So here you have put a soft iron sheet. So what will happen? The whatever magnetic field originated from the north, it will be prefer to go to the south of this iron sheet rather than going in the air and searching what are the other magnet you have. Now in this process what happened, the field lines after crossing through the soft iron, okay, if it is going through this, it is forced to come out and enter the south pole of the magnet to form in the closed loops. Okay, so in this process, the third point, which is this part, this region of this side of the soft iron shell is free. So there is no magnetic field, it will be observed. So it's completely shielded. This part is completely shielded. Is it clear? So I'll explain again. So here what is happening, you are giving, this is a magnet, okay, and these are the north and south pole. You are providing a iron sheet. So what is happening now? You know that magnetic field always go from the north and it is go to the south pole. So it is going from the north, okay, but it is here finding a iron sheet which is a very good magnetic material. It will try to enter here and force to reach the south pole to the magnet, and it form a closed loop. Similar thing you can see here, okay, that here you have a north pole which is giving the magnetic field here, and this is the equipment placed here inside this container. So here you have equipment X, and this is made of the soft iron container. So what will happen, this will go out here and be forcefully pushed to enter to the south of the another magnet. So this is how the X, there is no magnetic field, this is completely free from the magnetic field and our instrument is safe. Now in this video, just now what we have watched, that what is magnetic field, it is a force field region around a magnet where the magnetic force can be filled, and this you can see by the help of compass. Now let's see some of the question. Why are magnetic field lines closer at the pole of the magnet rather than the parts? So the question is that if you have a north pole and the south pole, why you are making the lines closer? Because at the poles the magnetic field are stronger, that's why they are closer. Now point number 2a, draw the figure 18.2, the magnetic field lines between the south pole of the two magnets. So this is the south pole of the two magnet you have. So you know the magnetic field always go outward from the north and it enter to the south, like this, like this. So here also it will be the same condition, that okay, it is going inside, doesn't matter whatever is there, but it is going inside and originating from the north pole. So they don't like each other. Okay, you can show this diagram like this, and again at x there is no magnetic field because the directions you can see they are opposite the neutral point. Now what about question number B? The circle in the figure it represents a compass. So this is a compass drawn in a circle to show the direction that compass needle points it. Okay, so if this is the magnetic field which is going outward from the north, so here what will happen, your north pole will be attracted to the south pole like this. Okay, so this will be diverted in this direction. So now let's see about the chapter number 18.5, which is talking about temporary and permanent magnet, which is a very important part itself. Okay, so in this topic they are talking about soft and hard magnetic material, as the name suggests, soft and hard. So it is not like they are very soft in touching. They are talking in terms of magnetic material, that who can magnetize very easily, who can magnetize, and it will take time. Okay, so if you think for example here iron and steel, okay, both are magnetic material. However, the magnetic material are different. Okay, so when you are saying that okay magnetic material is soft, what does it mean? It means it can easily magnetized and demagnetized, and hard means it's difficult to magnetize and so difficult to demagnetize. For example, iron in the soft and hard, you have a steel